In this video, we're going to discuss the inverse function of the exponential function. So let's kind of revisit and recall what we've discussed about inverse functions. First of all, we discussed not every function has an inverse function, and it's only the case that it has an inverse function if it's one-to-one, which means that each y value is only given by one x value. And the way that we determined graphically if a function was one-to-one was with the horizontal line test. Because if you can draw a horizontal line and it passes through more than one point on the graph, you've just found 2 points with the same y value, which means the function is not one-to-one. And therefore its inverse won't be a function, because when you switch the coordinates of all the points, you'll now have 2 points with the same x value, and it's not a function. So let's talk about our exponential function here. We discussed this in a previous video. The graph's going to basically look something like this if the base is larger than 1. And if the base is between 0 and 1, it's going to look like this. And we're approaching an asymptote to the right on this one and to the left on this one. So the graph is just either always increasing or always decreasing depending on our base. And if you imagine drawing a horizontal line through this graph, you're never going to pass through more than one point. And that kind of makes sense, because if you think about what the function looks like, if the function is 2 to the x, for example, if it wasn't one-to-one, that would mean you could plug in 2 different x values and get the same output. So doing 2 to one power and 2 to a different power is not going to result in the same value. So the exponential function is definitely one-to-one. And because it's one-to-one, as we've discussed previously, its inverse is a function. And back when we discussed inverse functions, we discussed that their graphs are reflections of each other over the line y equals x. And that's because to graph the inverse, we're essentially taking each point on the first function and switching the x and y coordinate at each point, and then the resulting function is the inverse. So let's use that to graph the inverses of some exponential functions and see what this inverse function is going to look like graphically. So we're going to start here with just a basic exponential function, y equals 2 to the x. In fact, let me use some function notation here. Alright, I'm just going to choose a few x values so we get a variety here, but we also will have easy points to plot then. So if we substitute each of these x values in, 2 to the negative 1, 2 to the 0, 2 to the first, 2 squared, there's our y coordinates. So we'll graph this. And as we've discussed before, this is going to increase rapidly to the right, and as you move to the left, it's going to decrease and approach the line y equals 0, which is the horizontal asymptote. We don't end up with any negative y values. That's going to be important to remember as we move into talking about the inverse. This exponential function did not have any negative y values. Okay, so let's graph the inverse of this function. We'll talk about the name of this function later. Based on the title of this video, you kind of have a spoiler alert. When I teach this in class, I haven't mentioned the name of the function up to this point. because really we're not doing anything new. We've dealt with inverse functions before. We've talked about what the table of values is going to look like for the inverse function. We're going to just take each point and switch the x and the y coordinates. So now we'll have the point 1/2 -1. And we'll have the point 1, 0, and 2, 1, and 4, 2. So let's plot those points. 1/2 -1 is going to be about there. 1, 0, 2, 1, and 4, 2. So this function also increases to left to right. It increases really slowly. The exponential functions increase quickly. The inverse of that increases very slowly. And then as we move to the left, let's think about what happens. Our exponential function did not have any negative y values, and 0 also was never a y value. So we only had positive y values. Now that we've switched the columns of the table, essentially, we're not going to have any negative x values, even if we had included more points, even if we included like 100 points, right? We wouldn't have seen anything other than positive y values for the exponential function, and so we're only going to see positive x values here. So what it means is this graph is never going to touch or cross the y-axis, because that would mean we had found an x value of 0 or a negative x value for over here in quadrant 3. So as we move to the left, this is just going to get closer and closer to the y-axis, but it's never going to touch or cross it. So the y-axis is serving as an asymptote for the inverse. So we have a vertical asymptote of x equals 0 for the inverse function. You can kind of see that symmetry that we discussed when we first talked about inverse functions. We said they're reflections of each other over the line y equals x, which is going to roughly look like this. And so you can kind of see that symmetry in the shape of the two curves as well there. Let's do this with another base besides 2, just to kind of see what the graphs are going to have in common and what's going to be different. So let's use 3 to the x. That first function we called f, so I'm going to call this one g. G of x equals 3 to the x. Just going to pick a few x values so we can get some points to work with. And so if we substitute those in, we'll have 1/3, 1, and 3 for our y values. And we know about what the shape should look like because we've studied exponential functions. We're going to have that horizontal asymptote there of y equals 0. So then let's graph the inverse. So again, we're just switching the x and the y columns. So we'll have the point 1/3 -1, the point 1, 0, and the point 3, 1. So this is going to be increasing slowly to the right, and again, we had no negative y values and no y value of 0. Only positive y values for the exponential function, so only positive x values for the inverse. So we're going to get the same vertical asymptote here that we did for the last one. And still seeing that symmetry over the line y equals x as well when we look at the shape of the curve. So we saw in the discussion on exponential functions that we always have that point 0, 1, right? We saw here that we had the point 0, 1 for the 2 to the x. We also had it for 3 to the x. Any base to the 0 is going to be 1. So we'll always have that point. And because of that, when we graph the inverse, we're always going to have that point 1, 0. So we saw that point 1, 0 showing up on both graphs. The rest of the points are going to be different depending on what the base is. We saw that for exponential, that's true of the inverse as well. You'll have the 1 point in common. The rest of the points are different, but the overall shape of the graph is the same, and the asymptote's going to be the same as well. Okay, so now that we've gotten comfortable with what the graph looks like and how we graph it, let's talk about what the name of this function is. So the inverse of the exponential function is called a logarithmic function. Sometimes we'll just call it a log function for short. And let's talk about the notation that we use. This is read log base b of x. Okay, let's start with base b. What is that talking about? Well, we used the word base to describe this value b when we talked about exponential functions. So since this new function is an inverse of that, it's going to have the same base. So if your function was 2 to the x, 2 was your base, so the inverse function also has a base of 2. And it's read log base b of x because remember x is the input, right? If you plug in a number for x, that's your input. We use the word of when we talk about other functions as well. Like when you talk about the function square root of x, x is your input that you're putting inside the square root. It's almost too bad that we don't have like a symbol for the log function like we do for square root, because I think with square root you get that visual, right? The x is inside of the symbol that we're using, and so it kind of visually tells you like, oh yeah, x is going inside of this function. That's the case here, even though we don't have a symbol that visually shows us that. X is the input. That notation out front, log base b, b is a subscript, by the way, on that log. So it's log and then a subscript of b. Log base b is just the name of the function, just like square root is the name of another function. So, like I said, if your base of your exponential is 2, like it was here, then the inverse function is going to have a base 2 as well. So this would be log base 2, so log and then a subscript of 2, and then we just write an x in line with the log part. So it's log base 2 of x. And then similarly, when we graphed the inverse of 3 to the x, that inverse is going to be log base 3 of x. So what is this log function? It's just the inverse of the exponential function. That's going to be helpful to keep in mind. Keep in mind how we graphed these before we even knew what the name of them was. Right? We took the exponential function, we switched the x and y columns. That gave us the log function. Now, kind of like we did for exponential functions, I want to kind of look at what's going to be the same regardless of what your base is. So let's start with a base greater than 1 because that's what we just drew for the first two examples there. We got the same basic shape, right, for both of those. For log base 2 and for log base 3, we got this kind of shape. It was increasing. We had this 0.10 that they both had in common because the exponential had a common point for any base as well. So we have this common x-intercept. We had a vertical asymptote of x equals 0 because the graph approaches the y-axis. It's increasing from left to right. Let's talk about the domain and range. We can see from the graph here that the entire graph is to the right of the y-axis, and that was the case because we said we're not going to have any any negative or zero x values. All the x values are positive. So since all the x values are positive, the domain is all numbers greater than 0. And the range, we can see from the graph, it goes forever up and down. And that's because the domain of the exponential was all real numbers. So remember, when you talk about inverse functions, the domain of one is the range of the other. So the exponential had a domain of all reals and a range of only positive numbers. The log function is the inverse, so those just switch. Okay, let's talk about what happens if your base is less than 1. We didn't graph that in this video yet. We graphed some exponential functions where the base was less than 1. Our bases are always going to be positive. But when the base was less than 1, this is what the exponential function looked like. It was approaching the horizontal asymptote to the right, as opposed to other bases approached it to the left. And if you can visualize your line y equals x here, let me draw that in. This is tricky to visualize, I think, but if we reflect this graph over the axis, it's going to look something like this. So since this one's approaching the asymptote to the right, if we reflect that over that line, it's going to be approaching the asymptote at the top. And then it's going to decrease this way. So that's going to be what the log graph looks like for a base that is between 0 and 1. Is really how I should have wrote that. So you still have the asymptote x equals 0, you're just approaching it at the top instead of the bottom. Still have the point 1, 0, because we still had the point 0, 1 on our exponential functions where the base was less than 1. We can see here the domain's still the same, only positive x's, the range is still all reals. Really the only difference between a base greater than 1 and a base less than 1 is that the function is decreasing instead of increasing. And that was the case for our exponential functions as well. They had the same domain, range, intercept that they have in common, and asymptote for all bases. It's just when your base is less than 1, it's decreasing. If a base is greater than 1, it's increasing. I did want to mention a couple of specific bases that are used a lot because these bases are so commonly used, they kind of get a special log notation in a lot of textbooks. So if the base of the log is e, and we discussed e previously, it's an irrational number, 2.7 something. It's a never-ending, non-repeating decimal because it's an irrational number. If the base is e, then you could write log base e to the x. Most books will instead write ln instead of log base e, and that's because we call this the natural log. So it's the same letters as natural log, just opposite order of how we say it. But x is still your input. This is just, ln is just the same as log base e. And then if the base of the log is 10, our book calls that the common log and uses just log. So if you just see log in our book or on your homework, that is log base 10. Different books, most high school and college books use these notations. There are some books out there that will use different notations. They'll use log to mean something else. And so if you're ever in another class not using this book, just be sure to know what notation they're using for what. But for our book, ln is log base e and log by itself is the same as log base 10.